Okay. So this is Boyle's law. So let's go to the one that says Boyle's law. See, P1 V1 equals P2 V2. Has ATM, it has millimeters of mercury, it has kilopascal. So let's see if we can do this problem. So on your paper, do P1 V1, P2 V2, and let's see what we've got. All right. So it says a 22.5 liter. What do you think that is? Is that P or V? It would be volume. So let's put 22.5. And it's at 740 millimeters of mercury. I'm thinking that's pressure, right? 748 millimeters of mercury is compressed to 725 millimeters of mercury. 725 millimeters of mercury, and it's asking us what the volume is. Okay? So our formula is P1 V1 equals P2 V2. What are we looking for? What are we looking for? V2. So to do that, you divide both sides by P2. That cancels that out. And so now we have changed the formula. I'm doing this according to science so that you can see it, and we're going to compare that to engineering. So I'm going to have 748 millimeters of mercury. I'm going to multiply that by 22.5, and I'm going to divide that by P2, which is 725 millimeters of mercury. All right, pull out your calculator and do your math. And tell me what you get. So that would be alpha Y inner. $23.21. And what is going to be my units?
Liters.
Liters. Now, does it make sense to you if you put it back in the equation, it should be equal, right?
Yeah.
That's the way to check it. So let's see what we got. So let's go 748 times 22.5. What do we get? $16,830. All right, now take 725 and times it by 23.21. I'm a man.
$16,827.20.
And it's pretty darn close, right? So, do you have all this written down, Kate? Okay, so now let's look on the next slide. So on this one, it tells us a cylinder is filled with 40 inches cubed of air with a pressure of 60 psi. The cylinder is compressed to 10 inches cubed. What is the resulting absolute pressure? Okay, so here we are again. P1 times V1, right? So let's do P1, V1, P2, V2. Now what I would like you to do is get your notes out for today. So turn your sheet to your notes. I would like you to write this down. So if we look, our P1 is 60 pounds per inch. And our volume is 40 inches cubed. Our pressure 2, we don't know what it is. And our velocity 2 is 10 inches cubed. So we're going to take ours again, but this time we're looking for P2. So let's see. P1 V1 equals P2 V2. If I'm looking for P2, does it make sense that I divide both sides by V2? So I'm going to have 60 pounds per inch squared, and I'm going to multiply that by 40 inches cubed, and I'm going to divide that by 10 inches cubed. All right. And this is the engineering part. Same thing, right? Except we just have different units. Now, is there another step that we have to do? Or is that the only step we've got to do? We're talking about pressure. So since we're talking about pressure, what did our notes say we have to do with our pressure? Yes. So that was the science way, but now this is an engineering way. So for my pressure, I have to add 14.7. Okay, so what is my new first pressure?
74.7.
74.7, right? Okay? That's the first thing I have to do. So make you a little note. That's the first thing I have to do. When I'm talking about Boyle's law, I have to check pressure. Pressure is only gauge pressure. It is not the pressure I'm looking for. So I have to add atmospheric pressure to get absolute pressure. Now I have it. Now I can do it. 74.7 times my volume 1, which is 40 inches cubed, divided by 10 inches cubed. Okay? That way is different than the way they did it on the PowerPoint, but this is the way I'm relating it to science. So, alpha y inner, I'm going to do 74.7 times 40 divided by 10. What did you get? 298.8. So 298.8. And so if we go in here and change our mode to scientific and do second answer enter, what do you get? I got 2.988 E2. Is that what you got? So the only thing I did is I went up and changed the mode, and I changed it to scientific, and I did second answer enter. Right? Yep, perfect. Now, what did they do here to get their answer to 3.0? They just rounded it up. That's all they did. So the difference between engineering and science with Boyle's law is we have to change to get absolute pressure, right? Besides that, everything else is the same. Is everybody good so far? Okay, let's go to the next slide. There you go. Answer the question, Eric and Amaya. You're gonna have to answer your question, Kate, but it's not gonna show on the screen. So the question is, what is the difference between the scientific formula and the engineering formula for this gas law? So type in what you think the difference is. And hit enter.
The one that we just did, was that science or engineering?
The first one we did was science, and then we went and changed it to the engineering. Okay? So the science one is on the Foursquare, and the engineering one was on the PowerPoint. Eric says they have different units of measurement. What besides that, Eric? One more time.
I said, that said the difference is you have to change the pressure in here.
Pressure is the main thing, right?
Sure.
But you're correct about, no, you're fine,
Oh, I can edit it so I can.
okay? So on here, the difference is, for Boyle's law, is pressure. We have to have gauge pressure plus atmospheric pressure to get absolute pressure. But besides that, the other thing, we have to change it to scientific notation, right? In science, we don't have to change it to scientific notation, but in this one, we do. Fantastic. Hey, yes, fantastic. All right, let's go to the next one. Charles's law. Let's get our little square out again. Flip it over to where it says Charles's law. Okay. So for Charles's law, we have volume 1, temperature 1, volume 2, temperature 2. The first thing that I tell my children that I'm teaching gas laws is the first thing you want to do is make this equation linear. If you make this equation linear, it will help you solve for the unknown. To make it linear, you're doing crisscross. So that's V1 T2 equals V2 T1. So write that out. Once you make it linear, you can get the unknown by itself. Okay? So let's look at the problem. It says calculate a decrease in temperature from 60 liters. So we've got volume 1, temperature 1, volume 2, temperature 2. So 6 liters is my volume 1, right? 6.00 liters. A temperature of 20 degrees Celsius. And it says, and is compressed to 4.0 liters. Okay. So what are we looking for here? Temperature 2. So, change my formula. How do I change that? Well, let's see. I want temperature 2. So if I divide both sides by V1, that gives me my formula. Is everybody good so far? So my new equation is V2 times T1 divided by V1. Are we ready? V2 is 4.00 liters. Multiply that by temperature 1, which is 20 degrees Celsius. And we're going to divide that by our volume 1, which is 6.00 liters. All right, let's put that in our calculator and see what we got. So, do alpha y enter again. 4.00 times 20 divided by 6.00. I'm going to change my mode back to normal. I get 13.3. Is that what you got? Okay. Eric typing it in, checking my math.
I'm still trying to.
you get there?
It says 40/3, won't give me. Can we just do 40?
Are you doing alpha y equal?
13.63.
Yeah, okay.
Yeah, I was doing that.
Oh, okay.
It was acting stupid for
It's doing friction. Okay, so it would make sense if I took this back in, so we have temperature 2 is 13.3. If I go back and I take volume 1, which is 6.00, and I divide that, let me do alpha y equal. I take 6.00 and divide that by my temperature 1, which is 20, I get 0.3. If I do my volume 2, alpha y equal 4.00 divided by 13.3, I get 0.3 also, so they equal out. Everybody good so far? Okay? All right, so let's look at engineering. So I'm going to leave that up there. So it says here, an expandable container filled to 28 inches cubed, and the air is sitting on an ice water that is 32 Fahrenheit. The container is removed from the ice and heated to 200 degrees Fahrenheit. Now, what do I have? Volume 1, temperature 1, volume 2, temperature 2. All right, what is my first volume? 28, right? 28 inches cubed. What is my second volume? I have no idea. Temperature 1, what is it? 32 degrees Fahrenheit. All right, what is my temperature 2? Okay. What do I need to change here? Well, you need to change the temperature, Miss Sloan, because your temperature can't be in Fahrenheit. It has to be in Rankins, right? So I'm going to add, what do I add to it? 460. I add 460 to that, I get 492. And for this one, I get 660 Rankins. What is the thing that's different in Charles's law? The temperature. We got to have it in Rankins. Okay. Write out our formula again. V1 over T1 equals V2 over T2. Cross multiply. V1 T2 equals V2 T1. What am I looking for? Volume 2. Divide both sides by T1. And there is my formula. So now what I need to do is just plug it in. So I have 28 inches cubed times 660 Rankine divided by 492 Rankine. All right. Eric, you do it and I'll do it and see what we get. What did you get, sir?
37.56.
37.56. If we changed it to scientific notation, because they like doing that, right? So 37.560975561. Mode scientific. Second answer, I got 3.75 times 10 to the first power. I'm going to change that to a 6. Is that what y'all have? See what they decided. Oh, did they give us an answer? They didn't give us an answer, did they? No answer. Well, that's the answer. It's 7.6. Excuse me, 3.76 times 10 to the first power.
No, not something.
37.56. Are we good? If I'm going too fast, I'll slow down. My thing is this. Make sure when you're going through the word problem, underline the numbers, write down your formula, make it linear, take it and solve for and put the unknown on one side, plug and chug it in. In engineering, they want it in scientific notation. Okay? Does it make sense? Once I got that number, if I put that number up here, I should be able to get those and have a check number. Everybody good? Okay. So, what is the difference in Charles's law?
The temperature.
Temperature has to be in Rankine. And also, and that's the difference, but when you're doing Charles's law, make the equation linear first, then get the unknown on one side. Okay. Oh, there it is. All right, here you go. What is the difference? Type that in, please.
Do I need to screenshot one?
No, yours is going to be on the one that's self-paced, and they don't. It shows me what you typed in there, but it's on another separate one. So when you're making a near pod, it can either be live or it can be self-paced.
That's how it's possible.
Yeah. Or we're trying to do this so that when taste class comes and you can't hear me anymore, better you can hear me but you can't see me, this will work. Okay, Charles' law, convert temperature into Rankines. Very good.
How will we have plexiglass in here?
Say what?
I guess,
Sides.
yeah, just in front of the desk.
Well, where would they go? Because we said you can do it.
It's going to be around, and that it's probably going to be on the sides.
Oh, yeah.
All right, baby. I like yours. I like yours better when you put the number, but we're all good. All right. Next one is Gay-Lussac. Okay. So Gay-Lussac has P1T1 equals P2T2. What do you think the first thing that you would need to do with that? Make it linear. Yep.
So P1, T2, P2, T1.
Right. So if it's P1 T1 equals P2 T2, it would be P1 T2 equals P2 T1.
That's the same thing.
Yes, ma'am. Okay. Now, in chemistry, in science, they use pressure just like they did with Bowles, temperature just like they did with Charles's law, except now what they're doing here is they're just combining them together. So give me a second. See if I can pull that up because I did not print it out for you. There is a blank space on your page on your squares. Please open that one up. And we're going to do the first practice problem that's on the screen here. So it says a sample of O3 is a rigorous vessel, has a pressure of 12 atm.
Wait, this one's
It's where your blank is. Yes, ma'am. You're just going to have to write the variables and stuff, okay? And if the gas is heated to 0 degrees Celsius to 25 degrees Celsius, what is the final pressure? Okay? We're looking for P2, correct? So write this down. So if we're looking P1, T1, P2, T2. So my first pressure is 12 atm. My first temperature is 0 degrees Celsius. And my second temperature is 25 degrees Celsius. So write that down. I have on the right. So what I'm going to do is I'm going to take my linear equation and I'm going to solve for P2. If I'm solving for P2, I would divide both sides by P2. P2 would be canceled out, and there is my formula. So I have P1, T2 divided by P2 equals T1. Next thing I'm going to do is plug and chug. So I have 12 ATM times 25 divided by 0 degrees. In my calculator, alpha y enter. I'm going to do 12 times 25 divided by 0. I can't divide by 0. So, what would I have to do with this since I cannot divide by 0? Oh, it says, remember, to convert Celsius to Kelvin, 273. Okay? 25 plus 273 is 297. So I'm going to change this. So my first temperature is 273 degrees Kelvin. It's down here. And 297 is here. Now I can do my equation. So alpha y equal 12 times 297 divided by 273, and I get, I get 1.3, oh, that's scientific. Normal. I get 13.05. So my answer is 13.05. If I take my 13.05 and put it in here, and I do my formula again, and I divide those, so if I take my P2 from my T2, so if I do alpha y equals, sorry, Kate, 13.5 divided by 297, I get 0.04. If I take 12 and divide that by 273, I get 0.04. So now I know my equation is right. Do you have this written down? Okay.
297 is incorrect.
Oh,
It's 298.
oh gosh. Oh my gosh, I can't add. Thank you, Eric. Change it then. 298. Well, I feel like I'm in Kate's way. 12 times 298 this time, 273, 1192 divided by 1 is 13.09. To do. All right, check my math there. All right, so that's Gay-Lussac's law as far as science goes. And so now I'm going to go back to the Nearpod example, and we're going to look at the formula that is here. I'll wait for Eric for a second just to make sure.
Yeah.
We good? Fantastic. So it says 300 inches cubed is sealed with the air tank sitting outside. In the morning, the temperature inside the tank is 62 degrees Fahrenheit, and the pressure of the gauge reads 120 pounds per inch squared. By the afternoon, temperature inside the tank is expected to be closer to 90 degrees Fahrenheit, What is the absolute pressure being at this point? Okay. So on this one here, they're using volume, they're using pressure, and they're using temperature, are they not? Okay? Now, which one did we not use?
We don't use the volume.
We didn't use volume. Why did they give us volume? Just to mess with us?
No, it's talking about the pressure inside of the air tank, and the volume is involved in the pressure.
It
You need
is.
volume to have pressure.
But is it involved in the Gay-Lussac practice problem?
No.
No, but it's telling us anyway, right? If we were using the combination gas law, would it matter? Yes, it would. The combination gas law has pressure, volume, and temperature. That's the other one that's on the other side. Okay? So let's see what we got here. So we've got P1, T1 equals P2, T2, P1, T1, P2, T2. So what is our first pressure?
120.
Where do we get 120 from?
Get it from.
The question, it is right there, isn't it? All right. We didn't have to do anything. Why did we not have to do anything?
Because it's already in pounds per square inch.
Exactly. Perfect. Thank you. What is our first temperature? Okay. 62 degrees Fahrenheit. Now, what is our pressure to? We don't know. Thank you, ma'am. What is our second temperature? 90 degrees Fahrenheit. Now, let's look and see what they've done. First of all, they converted the pressure, correct?
Mm-hmm.
So I wrote down 120, but if I add 14.7, it's 134.7. So let's change that. So the first thing they did is they changed the pressure of it. Next thing, we're changing the temperature. How are we changing the temperature? What are we adding to the Fahrenheit to get Rankine? 460. 460 plus 460. So I got 522. I'm taking theirs. 550. Does everybody agree? All right, so we had to change our pressure and we had to change our temperature. So, next thing we're going to do is we're going to make it linear, right? P1, T2 equals P2, T1. We are looking for T1, so we're going to divide both sides by P2. If we do that, we're going to have, I'm going to do it here, 134.7 times our temperature 2, which is 550, divided by our pressure 2, divided by our, temperature 1. Get it wrong. So sorry. Temperature 1 is 522. All right, let's do the math. Let's see what we get. Alpha Y enter. We're taking 1347. And we're going to multiply that by 550. Divided by 522. What'd you get, Eric?
141.92.
Okay, let's change it into scientific notation. And what is your answer now?
1.419 E2.
I have E3.
I had E2.
Okay, so I have 1.49 E3. If I changed it to E2, it would move the decimal over, right? Where'd they get 140 pounds from then? That's a different number we've got.
I'm pretty sure it's E2 and that thing just glitched because every other one before it's also been E2.
It has been E2. So if you look, our answer was 149.25. And if we did it, to the second power, that would move the decimal over, which would make it 149. And they rounded down. But I think 141 is the correct one. If you did the rounding right. Okay, so with this one, can I erase it? Sorry. Eric, you good?
Yeah, I'm going up.
Maya, are you good? Okay. So what I'm trying to do is I'm trying to show you two ways that they do it. I do it where I make it linear, and then after that, put my formulas in. They just go and do it crisscross. Either way's fine. What else did they do here? They had a question on the second part. Ask you how you got the absolute power, absolute pressure, but they wanted to know what the gauge said, right? So the only thing they did is they took their answer, they subtracted the atmospheric pressure to tell me what the gauge pressure was. Which you should be able to do that, no problem, right? Everybody good? Okay. How is Gay-Lussac's problem different than the science one? Like your answer, Maya? Perfect. Thank you very much for your participation. This one's going to be interesting for Maya. Okay, so the next one that we have, it talks about these common system of pneumatic. So what we have here is we start off with the compressor first. There's a relief valve here. That pressure is built up into this tank, which is transmitted through these lines, and then it will go down either to the regulator where the drain is, or it goes down to a filter and then a cylinder to be able to show that type of system. Next one. So it's asking you, look at the internet and draw in your ISM book. So let me show you what it really said, because you can't see it. And I thought it doesn't show you the name, does it, Eric? I am so sorry. I'm learning. Yeah, that's what you're supposed to be doing. That's why I'm letting you use your pads for that. I'm going to go back to the PowerPoint so you can see what in the world it's talking about. Okay, can you see the name on yours? Can you see a name on yours? Okay. Let me go back to my one. Mnemonic. Here we are. Boom. Well, I heard what you said. Okay, so you're looking for reciprocal piston compressor. Here's your picture. Draw something that looks like that. Just use your best judgment. A reciprocal piston compressor.
So just the drawback.
You're just drawing it. And you're gonna submit it. Well, it does work with the mouse. Can you do it with your finger, Eric? On your test string? Okay, cool. That's why I was using I'm glad she signed on to the computer so I can see the difference. You won't have to look at the internet for that. I'll show you what it looks like. Okay? So on this reciprocal piston compressor, you have pressure that's coming in. What is that? What is this right here? Cylinder, a piston, right? And then you have another piston out here, right? And you have a relief valve up here. And that's where the oil sits on the bottom. Fantastic. Can you also insert a text box?
Yeah.
Okay, put a text box. And what I would like you to do, ma'am, is I would like you to label that with a relief valve.
Oh, it just deleted that. Oh, that is so good.
I want you to label both of these as pistons. That is your reservoir down here. Reservoir. Okay, now come to you. It even make colors too, huh?
Yeah.
Cool. All right, you ready to label?
Yeah.
Okay, let's label. Okay, so up here is a relief valve.
Yeah.
Valve, V-A-L-V-E. Okay. And then over down here in the reservoir. What's that? How much was that? Okay, the reservoir is down there. There we go. Let's try another one. Oh, you want to do that one? You can add more than one? Oh, okay. Water. And don't matter if you spell it wrong or not, I won't know.
Okay.
And it goes down there. Okay? You have a piston here and a piston there. Piston, P-I-S-T-O-N. On each side, there is a piston. There's a piston here and there's a piston there. Okay? Reservoir, 2 pistons, and relief valve is what I want you to label. Okay? So your relief valve is here. Your reservoir is here. This is a piston, and so is that. And of course, these are lines. There we go. And once you get that done, submit it. All right. Go, Eric.
Edit words, please.
Reservoir on the bottom. And the lines are up the sides. And now I don't have to put the name of it in there when I figure it out.
exactly what I had to do back to that college.
Yes. Yep.
Do we need to have labeled 2 pistons reservoir?
Nope, one's good.
Oh, what else?
Submit. Perfect. Okay. So here's the next part, a rotary screw compressor. Can you see that on your screen?
I can see the rotary screw compressor.
Yep. That's what it's supposed to be, it's blank. So I need you to draw it now. So you are adding the rotary screw compressor. Let me show you what it looks like. The next slide. Everybody on the next slide? Go to the next slide, Eric. Okay. Here is your rotary screw compressor. Give me a second. I'm fixing it. Gotta go to the next slide. I'm at the next slide now. There we go. Now can you draw?
No, I think it's the next slide. This is telling us how to do it, so I guess the next slide must be.
Oh, no, maybe it's wrong. It's wrong.
Oh, it's wrong.
Yeah. So it's all right because I didn't edit it right. So if you're doing if you're doing the rotary screw compressor, it's going to look like this. Okay. So what it has is it has something like a bolt here that goes and it's attached to this screw here. And as that one turns, it turns this one. Exactly. You ever thought about that? Open a pencil sharpener, they have rotary screws. Very good, Kate. Thank you. I like that. All right, and let's see what the last one is because we're almost done. Okay, and then our rotary vane, which I can't believe you can draw that one either because I copied and pasted and I can't do that. So for a rotary vane, it looks like this. So what does that look like? Here's your, yeah, it's kind of like that. It's kind of like your fan that is in your car. Remember that? And you have water reserve on there. So we have our reserve there. We have this here. And then what do you think this is over here? Reservoir, exactly. It holds the extra in and pulls it up when it needs it. All right. And then, at least I got one video, one drawing. And then the next one is just the future of possibilities. What is this? It's a transport.
It's a tube pod.
So if I decide I'm here and I want to go to West Virginia, I just get in my little pod and it's kind of like a car, and it will actually transmit me there.
How long?
What does he use here? Air compression?
Uh-huh.
What if you got stuck in that?
Well, they use this already, except people aren't in it.
Yeah, they have test dummies thrown in.
No. Where do they use this at? Where have you seen this? Maybe you haven't. Huh? Thanks. If you go to the drive-through, they have a tube.
Oh, yeah.
You put your money in. Goes up, goes around there, and you take the money out and they send it back to you. This here is a pod per person. Don't think so.
They use test dummies on that. One went so bad that the test dummy was like as flat as paper.
Really? Did you see it?
Uh-huh.
What do you look up on YouTube for that?
It's just, I honestly don't remember. It was like a year ago.
Yeah.
It was on the featured page.
Gosh, that's awesome. All right, well, that's it, guys. That's it. We're done. I know you're excited about being done.